stability of hydrogen atom was a problem which remained unsolved for a long time. After Bohr's theory, the stability was explained. The stability of hydrogen atom was explained through Bohr's postulate. But the objection regarding Bohr's theory was that when an electron moves around the nucleus, it moves in a three-dimensional space. So the motion of the electron around the nucleus must be described in terms of three quantum numbers. But Bohr's theory introduces only one quantum number. The problem was partially solved in Sommerfeld quantization theory. But both the theory are unable to explain the intensity, both the theory, Sommerfeld theory and Bohr's theory, cannot explain the intensity of the spectral lines which are observed. To this end, the quantum mechanical treatment of hydrogen atom problem gives a satisfactory explanation. First, let me explain what do we mean by a hydrogen-like atom. In general, a hydrogen atom is a bound state of a proton Rp whose mass is mp and an electron of position vector Re and mass me. This is the hydrogen atom problem. You know the charge of proton Qp is plus E and that of electron is minus E. This is the situation. By hydrogen-like atom problem, we mean that we have a body of mass m1 situated at R1, and the charge Q1 is say it is either plus E. Then we have another particle mass m2, so that Q2 is minus E. It may be plus minus E, so it may be minus plus E. This is hydrogen-like atom problem. This includes the positonium atom, which is a bound state of an electron and a positon. Protonium atom, which is a bound state of proton and antiproton, and so on and so forth. It consider all this. It also accounts for helium plus atom, which is alpha particle plus one electron system, or it may also be lithium double plus system, in which case we have a nucleus of charge 3e plus 3e and an orbiting electron minus e. So there may be an n factor, another part was there. By hydrogen-like atom problem, we consider all these cases. In this case, we will consider that there is a nucleus for which the charge is Ze, and we have an orbiting electron whose charge is minus E. This is the hydrogen-like atom problem. Let me first write these two particles interact via Coulomb potential. These two particles interact via Coulomb potential, which is one by arc-type potential. We know from our knowledge of classical mechanics that two-body interacting system can be solved by introducing the center of mass coordinate and relative coordinate, and we describe the system as the motion of a hypothetical particle of mass equal to reduced mass of the system moving around the center of mass. Let us see what happens in quantum description. So we consider the time independent Schrodinger equation. For this we write the Hamiltonian of the system. So the system that we are going to consider, as we have described just now, is a system comprising of a particle of mass m1 and charge q1 is equal to Ze, and there is another particle of mass m2 and charge is equal to minus e. This is known as lab frame. So somebody is at rest in laboratory and he sees this system. The Hamiltonian is in lab frame. We have the Hamiltonian is the kinetic energy operator of the particle 1 plus the kinetic energy operator of the particle 2 plus the interaction potential. For this it is minus h line square by 2 m1 del the potential V is actually J in SI units Jd square by 4 pi epsilon 0 1 by R1 minus R2. Here the Laplacian operator, this means del x1 to del 2 del y and similarly for the other one. We want to rewrite this Hamiltonian. Before going to this, in lab frame, the time independent Schrodinger equation looks like Hamiltonian this is energy of the system. This is the time and this is the total energy of the system. So we write total energy of the system. We introduce center of mass Cm and relative coordinates. The center of mass coordinate is m capital R is equal to m1 r1 m2 r2 and the relative coordinate R is equal to r2 minus r1. Here we are interested in looking at the motion of the particle 2 with respect to particle 1. So let me introduce denote these things. This is R. R is directed from particle 1 to particle 2, and this is the center of mass coordinate, capital R. We have assumed that the particle 1 is heavier than particle 2, so the center of mass lies on for two particle system lies on the line joining the two particles, and it will be nearer to the heavier particle. So in terms of components, finally we have m is equal to total mass of the system. In terms of components, it reads like x is the x component of center of mass. It is m1 x1 plus m2 x2. M capital Y is equal to m1 y1 plus m2 y2. Capital Z is equal to m1 z1 plus m2 z2. And for relative coordinate, small x is equal to x1 minus x2 minus x1. Y is equal to y2 minus y1, and now let me write this one del x in terms of the new coordinates. So del x1, this is equal to del this one is m1 by capital M, and if we differentiate x with respect to x1, it is minus. As del x1, from this relation we get m1 by m, and del small x del x1 is equal to minus 1. So del 2 this is del x1 operating twice. So when this operates on this, we have m1 square by m square del 2 del capital X2. When this operates on this, we have plus del 2 del small x2, and this operates on this, and this we assume that the second derivatives are independent of the order of differentiation, so we can write it at thus. Starting similarly, we can write del x2 is del x2 del capital X plus for this part we write m2 by m del capital X if we differentiate this with respect to x2, it is m2 by capital M, and when we differentiate this one with respect to x, it is plus. So we get del 2 del x2 is equal to m2 square by m square del 2 del x2 . This is the term. Now you see that in this Hamiltonian there is one term 1 by m1 del x1, so we write 1 by m1 del 2 del x1 2 plus 1 by m2 del 2 del x2 2. Just we consider the x component of these operators, not the we are not considering the potential energy term right now. So this is this divided by m1, so 1 m1 goes, so it is m1 by capital M, and when we divide this, this is m2 by capital M square. So we have when we divide this, we have 1 by m1 plus 1 by m2 del 2 del small x2. This is multiplied by 1 by m1, this is multiplied by 1 by m2 and taken, and when we divide this, it is 2 by capital M, this is 2 by capital M, sorry, this sign will be positive. So this term cancels out. This term m1 plus m2 is m, so this is 1 by capital M. And this one we call it reduced mass, 1 by mu this is the reduced mass. For electron proton system, the mass of electron is the mass of electron m2. For electron proton system, proton electron system, mass of proton, this is 1836 in atomic unit, and that of m2 is 1, so that mu is nearly equal to 1, in which case we may assume that the nucleus to be the center of mass lies almost with the proton. For positonium atom, m1 is equal to 1 is equal to m2 and mu is just half. In that case, the center of mass lies right at the middle of the two particles. There are other atoms which as for example bound state of proton and antiproton is realizable, and other exotic atoms are there. You can find a list of them in any modern textbooks on quantum mechanics. Now coming to the Hamiltonian. The Hamiltonian now becomes the Now Hamiltonian becomes these two parts we first combine together. So this is minus h line square by twice m. Then there will be a factor like this, del del capital X2. When this term comes when we consider the y components. Now potential is a function of scalar r only, and we write it as this is the new form of the Hamiltonian. This represents the translational motion Hamiltonian corresponding to the translational motion of the center of mass, and this represents the Hamiltonian for relative motion. Now we rewrite with this we like to rewrite the time independent Schrodinger equation. So in terms of center of mass and relative coordinate, we have defined center of mass and relative coordinates here. So in terms of center of mass and relative coordinates, now the time independent Schrodinger equation becomes this psi total. Now this total is a function of capital R and small r only. Initially, when we wrote it in terms of the individual coordinates of the individual interacting particles, this was the wave function. Now we have recasted the Hamiltonian in this form. Now the variables are capital R and small r. So we write the wave function like this, and this is the new form of the Hamiltonian. You see the potential is a function of smaller only here. Before we have write for Hamiltonian this expression over here. The potential is a function of smaller only, so the equation can all easily be decoupled into coordinates involving capital R and small r. For this end we write here we have written the wave function as the product of center of mass, for product of function involving center of mass coordinate and relative coordinate, and we write the total energy E total as E of center of mass motion plus E of relative motion. E of relative motion. This would be better to write relative motion. So if we substitute these two, we find two equations. One equation is this, minus h line square by 2m. I am skipping the steps as you are well conversant with the separation of variable techniques. Sorry. The potential energy term this equation represents the motion of Cm. This represents the translational motion of the center of mass, and this governs the relative motion. Our aim is to find the stability of atom, to address the stability of atom problem from quantum mechanical viewpoint. So we go to the center of mass coordinates. When we look at the system in center of mass coordinate system, this is the equation of motion in center of mass coordinate system. In center of mass coordinate system, the observer could not identify the translational motion of the center of mass, so we can assume this to be not there. So the relative motion is governed by this, and we can rewrite this equation now, dropping the subscript which were used to remind us at every step that we are considering the relative motion. So the equation in center of mass coordinate, the equation becomes where E is the energy of relative motion. So by introducing the center of mass and the relative coordinate, we can decouple, or we can convert the two-body interacting system into an equivalent one-body problem. This is an equivalent one-body problem. The original problem is now reduced to this. Now our objective will be to solve this equation keeping in mind that this gives you the relative motion, that is the motion of an hypothetical particle of mass equal to the reduced mass with reference to the with respect to the center of mass. So the R represents the position of particle 2 as viewed from particle 1, and entire system is being viewed from the center of mass system. So this is the situation. Now we shall consider this equation only. So in center of mass coordinate system, the hydrogen atom problem is reduced to an equivalent one body problem. Time independent Schrodinger equation for relative motion is plus the potential energy. Note that the potential energy is a function of scalar r, so it is a central potential. So we can apply the potential is central one, and we know that it is formed in SI system of units. This is Z E square with a minus sign by 4 pi epsilon 0 r. This is the potential, and for we can as the potential is central, we can assume we can apply the theory that we have developed for one dimension for spherical Schrodinger equation when applied to spherically symmetric problem. This Hamiltonian can be written in terms of L square operator, and a radial part, and the angular part is taken care of by the angular radial part, and the angular part is taken care of by L square operator. And let me write this in brief. I am not using the explicit form of this, but just writing it as B. There will be one more part, L square operator. R square, this is for this part, plus the this Hamiltonian commutes with L square and Lz, as we have already argued. So the Hamiltonian now becomes this is the Hamiltonian. Hamiltonian commutes with L square operator, and it also commutes with the Lz operator. We know from our study on angular momentum that spherical harmonics is the simultaneous eigenfunction of L square and Lz. So L square operator has its eigenfunction as L into L plus 1 H line square YLM, and Lz operator so we can argue that H, L square and Lz will have a simultaneous set of eigenfunction. In this, keeping this in mind, we write it as the radial part times YLM of theta phi, YLM of theta phi. And this equation becomes the R equation. As we shall see that R equation depends on the energy as well as on angular quantum angular orbital angular momentum quantum number. So we write it this as the wave function, and furthermore we write REL of R is equal to UEL of R by R. So and with the requirement that UEL at R is equal to 0. So at the origin it is of the form 0 by 0. So capital R, the radial wave function, is finite at the origin. For atomic system this should be 0 because the electron cannot come to the nucleus. And if we consider the differential equation in terms of U is 1 H line square by twice mu d2 U E L dr2 V effective of R This is the differential equation that is satisfied by the reduced radial wave function, this for every central potential, where V effective is defined as V of R plus L into L plus 1 This is known as the centrifugal barrier potential, and this is the effective potential. And if we consider the Coulomb case, this part is minus Z E square by 4 pi epsilon 0 R. Then the curve will be like this. This potential for L is equal to 0 is 0, for L not equal to 0 it is and dies after some time, and this potential is a long range potential. This is V of R, and so the effective potential is found to be of this sort. This is V effective. This is the effective potential. If we see that the potential is repulsive at small r, which prevents the electron from coming to the nucleus, and it is attractive in long range for long r. So our problem now reduces to the solution of this equation where P effective is given by this. I have missed a term. This. So our problem is to solve this equivalent one-dimensional problem. So let me first summarize what I have done or we have done in this class. Firstly, the two-body interacting system, which was a six-dimensional problem, was reduced to equivalent one-body problem when we introduced center of mass and relative coordinate and described the relative motion. So this is a three-dimensional problem. Since the Hamiltonian for a central potential commutes with L square and Lz, so that we argue that the Hamiltonian L and Lz and L square will have the simultaneous eigenfunction. We already know that L square and Lz has their eigenfunction in term as the spherical harmonic. So we rewrite the total wave function for relative motion as this, and so the three-body problem describing the relative motion now reduces to a one-body problem. Now our aim is to solve this one-dimensional differential equation for the potential governed by this. It will be taken up in the next class.